Hello, this is Timothy Wood with Citadel Civil Engineering. This is CIVL202 Statics, and in this lecture, we're going to go over a brief review of terminology and laws and units that hopefully we all picked up in your physics class. So Physics 1. So hopefully this is a review for you. It's also covered in chapters 1.2 to 1.4 of your textbook if you want to be following along there and checking on your notes. Now, just as a reminder, this is how the course is laid out, and here we are. We're actually doing some of the groundwork so that we can talk about force vectors within the context of a particle. But that brings us to a lot of terms that are on this screen that you probably don't know exactly what they are yet. So let's clean that up by first talking about models. Now, hopefully you've already watched, or if you haven't, you'll soon watch the model where we talk, or the video where we talk about how reality behaves one way. We have mental models that let us think about the problem another way. And then we have engineering and math models that let us actually predict behavior. Within that engineering and math model, and a little bit within the mental model, we have simplifying assumptions that we make where we generate those engineering and math models. And we use these words to provide kind of a shorthand clue as to what we're doing there. So the first type of model we might have is a particle. So you can see on our little roadmap that we can talk about a particle. And when we model something as a particle, we're modeling a body, so a thing, where we are considering its mass at a point. I'm abbreviating point PT right there. So we're looking at a mass at its point, and we're neglecting its size and shape. So at that point, no pun intended, when we think about a particle, we're saying, okay, I'm going to, instead of dealing with all the complicatedness, I'm going to have it be a mathematical point where I keep track of its mass and I neglect everything else. Now that will let us do a whole lot of really cool things. It's a useful model. It's really wrong. Things aren't actually mathematical points, but it is very useful for a lot of applications. Now, when that becomes less useful, we change our model. And so we'll go to a rigid body. And a rigid body, again, it's a body, just a thing, has mass that we care about and shape or size, typically modeled using length, but we neglect any flex. So that any 2 points on a rigid body are always going to be the same distance apart. It's always inflexible. So we model it as inflexible. And now it turns out that most things are actually flexible. They may only be a little bit flexible, but they'll be flexible. So for example, to take a completely normal object, we might have something like a water bottle, and we can model it as a particle, only think about its mass, or we can model it as a rigid body, only think about its mass and shape. But we would notice that if I squeeze it, it does give a little bit. And so it's not actually a rigid body, but we can model it as a rigid body. So that's how we might model some bodies. We might also model forces in a couple of different ways. So we could have a concentrated force, like so. And when we think about concentrated forces, they're going to be forces at a point, no contact area. Okay, so if we actually applied a force at a point, if we took a knife and we pressed on that knife edge and we focused it down on a point, we would actually cut things. So that's not actually accurate, but sometimes for different problems at an appropriate scale, we can model it as a force, a push or pull, applied as a mathematical point, and that's just fine. So that's a concentrated force. In reality, we have something more like a distributed force. And now we're thinking about that push or pull again, but we're going to model the force as a pressure. That would be in 3D, or line load. That would be in 2D, where we do care about with the contact area or contact length. And so again, if I have instead of a knife's edge, I take my hand and I press on something, there would be a pressure acting across my hand that we could model as a distributed force. Or if we were backed up far enough, we could model it as a concentrated force, even though we actually know it's more like a distributed force. So those are some of our forces. Within these forces, we're going to have two different types of forces, which we will pencil in right here. So we're kind of continuing and flowing over to the side. We'll have loads and we'll have reactions. Loads and reactions. So these are forces, the push or pull, but there are different ways of thinking about these push or pull. So a load is going to be a force applied to a body, whereas the reaction is going to be forces from supports that resist motion or resists loads. So this becomes very important when we start designing structures to recognize that some of our forces, they can be concentrated forces or distributed forces. Some of them are loads. They're applied to the structure. So we can think of things like self-weight or vehicle traffic acting on a bridge. Those would be an example of loads. The reactions are going to be forces, still a push or pull that could be either concentrated or distributed, but they're going to resist the applied load. So this would be the support from the foundation holding up a bridge. Those would be examples of reactions, forces that way. We'll also abbreviate reaction in this class for the sake of expedience with the abbreviation RXN. Okay, so that's some of our terminology. Hopefully that's starting to sink in. Hopefully you saw that in your reading. You maybe even had it in your notes already, but this is how I would shorthand these things. Now, once we have these terminology in place, we can start thinking through some of our other physics terms. So this is this is Newton, Isaac Newton. Isaac Newton really started much of what we would call common engineering today. He believed, as do I, that we live in a world that is repeatable because we serve a God who is repeatable, that's created things to work in a predictable and repeatable fashion. He wrote a book called Newton's Principia, where he outlined these things. One of my personal heroes is Nathaniel Bowditch. He was the father of modern naval navigation around the Revolutionary War period. There's a great historical fiction kids book called Carry On, Mr. Bowditch that I recommend you all read. It's fantastic. He actually taught himself Latin simply so that he could read Newton's Principia. So it's a fantastic book, and he outlines these things. Now, hopefully you already know Newton a little bit, and you can tell me what Newton's three laws are. Now, three laws of motion. Maybe you can't, but if that's the case, we'll review here. So what's Newton's first law of motion? Well, commonly we say the sum of the forces equal to zero, or this would be his law of inertia. So an object in motion stays in motion, an object of rest stays at rest, unless acted upon by a net external force. Sum of the forces equal to zero, and yay, nothing moves. Newton's second law says that the sum of the forces is equal to the mass times acceleration. This uses vector quantities, hence those little hats. If you're not sure what that is yet, don't worry about it. We'll get there. But we're going to say sum of the forces equal mass times acceleration. This is what you're going to spend a lot of time studying in dynamics, is Newton's second law. Newton's third law says that for every action, there's an equal and opposite reaction. So we're going to have action, reaction. Now you'll notice we've actually already talked about action or reactions down here, forces that support or resist loads. So loads, that's our action, something pushing on a body, and the reaction, something pushing back to keep it in place. And generally, if we have two bodies interacting this way, so here's my two bodies, I'm drawing them as circular, rigid bodies, so they have a little bit of shape there. If they're acting against one another, Newton's third law tells us that these forces will be collinear. which means that they're going to act along the same line, that action and reaction. They're going to be co-linear, like so. They're going to be equal in magnitude. Hence, I've drawn these red lines that are going to become arrows in just a second. They're going to be equal in magnitude. So F1 is equal to F2. And they're going to be opposite in direction, such that if F1 points in the positive direction, that is assuming that I've put a sign convention on there, that F2 is going to be equal in magnitude pointed in the opposite direction. So to write that in vector form, we'd say that F1 is equal to a negative F2, again with those vector hats indicating they have direction. Don't worry about it too much yet if you're not quite with me there. But the idea is that Newton's third law tells us that for every action there is a collinear equal and opposite reaction. So that's Newton's third law. Of course, all of these things combined together give us the idea of gravity or weight, which you can read about in your textbook, the base form, but we're going to typically think about this in terms of weight is equal to mass times gravity. So weight is equal to mass times gravity, where gravity is the acceleration due to gravity. G is going to be 9.81 meters per second squared in SI units, and it's going to be 32.2 feet per second squared in US customary units. And if you forget those numbers, that's okay. They're on the first page of your FE reference handbook. So hopefully you've got that FE reference handbook with you and you can identify G. Now I've written that over there underneath derived units because I want us to walk through the various types of units that we have. So when we think about our various types of units, we've got two systems of units. We have SI, which is the international system of units, and we have the US customary units, which is the US form of units. You may be familiar with one more than another, but we'll notice that in each case, we're going to have to measure length. SI uses meters, the US customary uses feet. Sometimes we'll use inch or miles if we need either smaller or bigger than feet. SI and US customary both use the same unit for time. Praise the Lord for that. Seconds are seconds everywhere. When we talk about mass, SI gives us the kilogram, and US customary units gives us the slug. And then when we talk about force, so again, that push or pull as a concentrated force is going to use either newtons or pound force. Now, when we come up with a system of units, you're going to have to develop some arbitrary units. So in this case, our arbitrary units in SI are length, time, and mass. And then we look at this Newton's second law to help us derive that final term, force. So using F equals ma, we can talk about the derived unit, the Newton. With a Newton, we're going to have our weight in newtons, and then we're going to have our mass in kilograms, like so, and then our acceleration in meters per second squared, like so. So 1 Newton is equal to 1 kilogram meter per second squared. That's our derived unit there. When we talk about our SI units, our fundamental unit is the US, our assumed units, our arbitrary units, are feet, second, and pound force. I'm going to use pound, LB, only meaning force. Civil engineers sometimes like using kips, kilopounds, which uses the SI prefix kilo and attaches to a US customary unit, pound. So a kilopound is 1,000 pounds, because when we design buildings and bridges, if our design is plus or minus 1 pound, we are shaving it way too close. If it's plus or minus 1,000 pound, that is sometimes more convenient for us. But when we do that, our derived unit is going to be the slug. And so again, we're going to put our units in here into our Newton's second law, F equals ma. So we're going to get pound force, or pound, LB, is equal to a slug times feet per second squared. And then we've arbitrarily assigned what a pound is, a foot is, and a second squared so that we can see that a slug is equal to a pound second squared per foot. You don't really need to memorize that. Most of the time, if we need slugs, we'll just leave it as pound second squared per foot in our unit analysis throughout. Now, what that does mean is that there's sometimes this unit here called a pound mass, which is equal to 132.2, 1 over 32.2 pound or slugs, pound second squared per foot, such that when we plug in 1 pound mass and multiply it by 32.2 feet per second squared, we end up with a weight of 1 pound force. But again, this makes all of our other math a little dicey. So that's one of the things to keep in mind there. Now, remember, one of the things that we're doing is that we're hopefully building a mental model that can handle things like how we model bodies and forces, that can think through Newton's laws, they can identify whether we're applying the loads or we're reacting, generating a reaction, and that would also connect to just how big it is. So one of the things that's important about units is to recognize that engineers always use units. Always. So every single time you work a problem as an engineer, you write a number down, you're going to write its units afterward. You can treat those units like variables. Engineers always use units. You can treat those in those units as variables. They'll cancel each other out, they'll carry around, and hopefully you'll get the right units at the end. Especially in fluid dynamics, we do a lot of unit analysis to learn how things work. So we're always going to write our units down. But we also need to have a good mental model. So if you look in your FE reference handbook under the unit conversion, you'll notice that 1 pound, I think many of us know what a pound is. If not, you can think of a soup can. A typical soup can is around a pound. And we can compare that to a Newton, and you'll notice that there are 4.44 Newtons and some other numbers per pound. Now, when we think about that, I want to get a good mental model going for you here. So what you're going to do is next time you go to McDonald's, you're not going to order a quarter pounder with cheese. Instead, you're going to order a 1 Newton with cheese. So that's how big a Newton is. So you think of that little meat patty and you think about it cooked down because it's a little less than a quarter pound once it's cooked down. That's the size of a Newton. So hopefully now you know how big a Newton is, you know how big a pound is, and you know what a slug is, even though you never want to use it again. Hopefully now we've covered some of these review pieces. We'll know what we're talking about, particles versus rigid bodies, when we talk about our bodies. We'll know about concentrated forces versus distributive forces and whether they're loads or reactions as we think about our forces. We're going to remember that we're using Newton's law. Newton's third law is going to be super useful for us. We're also going to be able to talk about Newtons as our derived units. Slugs we won't really use, and we're developing those mental models that relates a pound, about a soup can, to a Newton, a quarter pounder with cheese. Hope that's helpful to you. I look forward to seeing you in class and seeing what your notes look like. Take care. We'll see you then.